I would like to welcome you all in this session, in which we are going to demonstrate how we can build a digital protein formulations framework based on the groundbreaking advancements in the field of artificial intelligence from Google side and the physics-based modeling internally developed inside Siemens. Why did we pick a subject as complicated as that, as protein formulations? Well, first of all, its wide applicability. The pharmaceuticals, personal care, food are just few of the industries that we can find protein formulations. And it's recently estimated that around 20% of new drug discovery is in biologicals. Also, early stage diagnosis of pathological diseases are directly correlated to protein aggregation, which is just a subcategory of protein formulations. And the reason why we go into a digital twin of protein formulations is because one, the 3D protein structure could take up to a year to be experimentally determined. And that is even if we have the state-of-the-art in laboratory techniques. Even with X-ray crystallography, the protein should be isolated, crystallized, then X-ray should be applied, and that is barely 1% of the process. Another very and equally important issue is that high protein concentrations can lead to unwanted physical behavior. And this is something that you cannot really have in the drug development stage. Lab scientists should be aware of it in the drug design space. Hence, virtual screening tools and bioinformatics and modeling is required so that you could screen against many different molecules that they prevent such kind of behavior. But even in the digital world, we do have a lot of challenges. One is how do we go from a protein sequence to the protein structure? Well, this is, as I mentioned, a challenge for the experimental world as well. And in theoretical biophysics, this was a problem for around 50 years, where people tried to solve using physical interactions, the statistical molecular simulations approach, and at the same time using the evolutionary road, where the past and the present of the protein was taking into account its homologs and many different bioinformatics tools that should be integrated with physics and chemistry constraints to predict the structure. Another very important issue when it comes to molecules as big as that, we are in the range of kilodaltons, is the interactions themselves. And by interactions, I mean the widely known electrostatic interactions, hydrophobic interactions, but the very specific ones and very challenging ones, specific interactions, like hydrogen bonding, like pi stacking, and so on and so on. And finally, equally challenging, the system itself. When we do deal with biomolecules, we have phenomena like binding, like titration, denaturation, very complicated phenomena that arise in many different conditions, in many different stages, and in many different time and space scales. To account for all that, we really need a very accurate and fast model, especially if we are dealing with industrial applications. Today, I'm going to present the solution that we have inside Simcenter Culgi to create essentially a digital twin, starting from the sequence to simulating essentially any kind of system we want. And the solution going from the protein amino acid sequence to structure was recently provided by Google. They developed the AlphaFold 2 an algorithm that essentially solves the protein folding problem by incorporating multiple sequence alignments into a neural network built and created to solve graph inference problems, so that each and every amino acid sequence is placed as accurately as possible in space by minimizing a loss function that was trained against around 200,000 already experimentally known protein structures from protein data bank. When it comes to interactions, there are many ways of solving the problem, but if we try something like ab initio calculations, DFT or Hartree-Fock, then that will take a lot of time, even with supercomputers and clusters and cloud solutions. So internally inside Siemens, we have recently developed a solution. We call it ABC. It's essentially a bond charge correction, accounting for the misrepresentation of dipole moments in the electrostatics of semi-empirical Hamiltonians, like AM1 semi-empirical solution, so that we can get as close as possible to DFT results, but with a fraction of computational time. For the system itself, we have a different algorithm, a second algorithm internally developed inside Siemens, the automated fragmentation and parameterization protocol, in which many atoms, one can select how many are placed in one interaction site in one sphere, let's say, and the molecular detail, the atomistic detail, and the quantum chemistry detail is transferred to the mesoscale representation, as we call it. We do that so that we can simulate systems that arise in even millisecond scale and micrometer space scales as fast as possible and as accurate as possible. Here, for example, you can see an avidin molecule binding to structavidin. This is a known complex, and this is a simulation that can be performed in a modest computer with our solution. So with these three algorithms, AlphaFold, ABC, and AFP, we have a full solution, and we have created a digital twin for the protein formulations problem. And that gives us many benefits. It offers us new protein formulation design opportunities, as we really extend the protein chemical space as it has never been done before. It allows us for virtual testing of biosystems in their molecular detail, and we can optimize or modify existing formulations. And that is, for example, if we do see protein aggregation, then we can introduce specific molecules to hinder the process, or at least limit the spread of it. To showcase our digital twin, our digital pipeline, I'm going to apply the whole methodology into studying the neurofilament light chain protein aggregation. Neurofilament light chain is a very important biomarker when it comes to multiple sclerosis, which is a very severe neuroinflammatory disease, and the protein structure was completely unknown to the scientific community up until AlphaFold 2 predicted it computationally. We ran the DeepMind, the AlphaFold 2 algorithm developed by DeepMind, which is Google's startup, and we see the tertiary structure where you can observe the dark blue color, then the model is very confident that the amino acid is correctly placed, and this is profoundly for the alpha helix, while when you see a green color appearing for the beta seeds, then the model is not that confident because these strands are far more flexible in space. The same observation we can have from the local distance difference test, where for the range of the position 100 to around 400 amino acid sequence, you can see a confidence interval of around 100%, which really accounts for the alpha helix regime. To get into the place to simulate and model the protein aggregation, we have to start from the atomistic representation. This is provided from AlphaFold 2. And then we want the interactions. We want the electrostatics, the dipole moments, and so on. And for that, we use the board chance correction algorithm internally developed inside Siemens. Here you see the electrostatics profile of the studied protein. And then all this information needs to be transferred as precisely as possible to the mesoscale representation coming from the automated fragmentation and parameterization protocol that we have also developed. Now, we thought that it would be nice if we also couple the medicinal chemistry interactions that we know for more than 30 years inside the scientific and industrial community, where for each and every interaction happening, no matter if this is electrostatic, hydrogen bonding, hydrophobic, pi stacking, we do know what is the shift or the change in the energy levels. You see, for example, for many different interactions, what is the energy range. And we really need to take that into account because, for example, an 1.5, 1.4 kilocal per mole change would also lead to 10% to 10 times change in a drug's potency, which is something significant enough to take care of. These kind of interactions were also incorporated in the model, and then we were able to simulate neurofilament light chains protein aggregation. Protein aggregation provides crucial insights on the onset of pathological diseases, and as we already mentioned, it should be taken into account in the early drug discovery stage so that we avoid any kind of problems and issues in the drug development itself. And in the molecular level, protein aggregation is an outcome of the disulfide bonds acting as cross-linking agents between polypeptide chains. You can see in the left simulation box the neurofilament light chain solution in 10 nanomolar concentration in aqueous environment. And if I run the simulation, if I run the movie, you will see that essentially no aggregation really occurs. Now, if in 100 nanomolar concentration, the proteins are closer together, far more opportunities to form this kind of bonds. And you see, I just zoomed in, two proteins, they formed a disulfide bond, and protein aggregation was initiated. So after this kind of demonstration, I would like to leave you with few key takeaways. What we have done here today is that we have developed an automated digital framework for the design, test, and optimization of protein formulations. And if someone uses that kind of framework, it could accelerate drug discovery by screening over many new drug candidates virtually. It can inhibit the progress of neuroinflammatory diseases by preventing protein aggregation in early design stages. And of course, we can explore new protein groups as conditioning agents in many different industrial sectors, including cosmetic and food. I would like to thank you very much for your attention.